All right, we're going to do a quick example of how to find the moment of inertia of an I-beam cross-section about a horizontal line that goes through its centroid. First thing we want to do is be able to find the centroid. Now for an I-beam, this is pretty easy because remember a centroid lies on the intersection of the point of the two lines of symmetry for the cross-section. So since an I-beam has two lines of symmetry, the centroid will be right in the geometrical middle of this shape. Okay, next we want to be able to find the moment of inertia about this horizontal line that goes through the centroid. I'm going to break this up into three pieces. There's a top flange, a bottom flange, and then this web that's in between. We're going to need to use the parallel axis theorem. And if you remember, the parallel axis theorem says that the moment of inertia about any position is equal to the moment of inertia about the centroid of that object plus the area of that object times the distance between the centroid of that object and where you want to calculate the moment of inertia about. In this case, we want to calculate the moment of inertia about this line, which lies at a distance of, looks like 7 inches from the base. The entire I-beam is 14 inches tall, so that would make this distance 7 inches. Okay, so we're going to add the contribution of the top flange. Now to find that about the centroid of the entire cross-section, the moment of inertia contribution is 1/12 the base, which is 10 inches, times the height cubed. Now we want to transfer that by multiplying it by the area, which is 10 by 2, times the distance between the centroid of this section and the distance, the centroid of the entire cross-section. It's 5 inches from here to the bottom of this flange, and another 1 inch. So that would make this 6 squared. Piece number 2 being in the middle, we have 1/12 the base times the height cubed, plus the area. But the distance between the centroid of that piece and the centroid of the entire cross-section is 0. So this whole term will go away for the center web. Plus 1/12 the base times the height cubed of the entire flange down here. And then the area of the flange times the distance between the centroid of the bottom flange and the centroid of the cross-section squared. Real quick, let's go ahead and find a number for that. So calculating these numbers out, I get for the first moment of inertia term 6.667 inches to the 4th power. And then the AD squared term is 720 inches to the 4th. The reason why an I-beam is so often used in structures is that by taking this flange and separating it far away from this neutral axis or the centroidal line, we can greatly increase the contribution of the moment of inertia of that flange to the cross-section. Notice that this AD squared term is really big. That's what I'm saying. The AD squared term is really big, 720 inches to the 4th power. That's much bigger than just the contribution of the flange itself to the moment of inertia of the entire cross-section. By separating this distance further and further apart, we can get a big increase in the moment of inertia. So 6.667 plus 720 for the piece 1, 83.3 for the middle. And the bottom flange has the same contribution as the top flange for the I-beam, so I'll multiply that by 2 and add that to 83.3. So for this one, I get 1,000 537 inches to the fourth power.